we've got to figure out how to do math problems here with friction now. So you did an experiment, virtual as it was, where you had to pull blocks of wood or blocks of glass or whatever, one thing on another. This is taken from wood on the table, wood on a lab table, which is wood on wood. This section of the graph right here, that was when it was not moving. This was the static friction part. Notice it is a range from 0 up to a max. It's whatever it has to be so the block or the object does not slide. And if you push with 1, and I showed you this in a previous video, where if I push the side here, if I'm pushing with 1, it doesn't slide, the friction of the static friction is 1. I push with 2 and it's not sliding, the static friction is 2. And then at some point, boop, it breaks free, and that's the maximum static friction. And you had to read that off this graph. Some of you did a great job. Some of you need to go back and redo it to get a satisfactory. But if you look over here, this is like right there. 1, 2, 3, 4.3. It's 4.3 newtons is that maximum static friction. And then it breaks free and slides. This is sliding or kinetic friction. And it's a range, it catches frictions due to irregularities. So sometimes it catches, it releases, catches, it releases. So it's a range, but it's generally in the middle of that. And it's consistent. It's constant, where static can vary from 0 up to a maximum. Kinetic is generally one value. And that's about, in this case, 1, 6, 7, 8, 8.5, 1.85, right? 1.85 newtons, I'm thinking, for that. Let's add another 0 there. Significant digits wise. So that's how you read that, and that's what these values tell you, and it's important to realize static is a range. It can be whatever it takes to not slide, and then there is a specific point at which it releases. Kinetic is pretty much a consistent value. All right, that was reading it. Then we got graphs like this. Now, I did this one a little different than what you would have got, but it's the same idea. This is the static, the max static graph. The maximum static friction for all the materials and all the experiments is always bigger. It's always bigger than the kinetic. Maximum static is always bigger. And it was consistent when we compared it to the normal force. We got a linear regression, a direct relationship between normal force and maximum static friction. Likewise, for the kinetic friction here, this one's kinetic. We had a linear regression there, which shows a consistent direct relationship between normal force and the frictional force. Now, the equation for a line, as you all should know, is y equals mx plus b, right? Where y and x are your axes, your variables, and m is your slope. So we can see here for static friction, we've got a consistent slope, a consistent relationship between normal force, our x-axis, and max static, our y-axis. Likewise, for kinetic friction, this is the normal force, the x, and this is the kinetic. The y. These intercepts are really small compared to the values, right? It's negative 100th, negative 300ths when we were doing things at like half a Newton, 1 Newton, 2 Newtons, at whole Newtons. So it's on the order of 1/100th as much. It's essentially zero. It's essentially zero. So what happens is we get these relationships. We get a relationship here for kinetic friction that the friction kinetic is equal to some constant, the slope, times the force normal. Well, that slope depends on the material. In this case, it was wood on wood. You might have done glass on glass or graphite on graphite or whatever the options were. You had a lot of options that experiment. Well, this slope is specific to the material, and it's called the coefficient of friction. Coefficient of friction. So this equation becomes Fk equals mu k Fn. Coefficient of friction is represented by this Greek letter. Whoop, let's show you that a little better. Greek letter mu. Mu. It's a funny looking U. It's actually the M. It has a leading edge to the U here. And then a subscript K for kinetic. That is mu. The coefficient of kinetic friction. So it's just like y equal mx plus b, but there is no b, right? It's the slope of that line. And if you did your experiment right, you got nice straight lines like this. If you didn't get straight lines like this, you made some mistakes in reading your data, and you'll need to redo it. It's not satisfactory unless it comes out right, because it's pretty easy lab actually. All right, so we get this equation that can tell us kinetic friction. And likewise, for static friction, we got that same thing. But this is only for max. We've got Fs max equals us Fn. So that will tell you the maximum amount of static friction right when it breaks free. Now you have to be careful. You can only use that if it says it just began to slip. You pushed it until it slipped. The hardest you could push without it beginning to slip. Something that tells you it's right on the verge of about to slip or just began slipping. And then you can use this equation. Otherwise, static friction's a range, right? Remember your data. It could be something less. If you're not making it slip, it's going to match whatever you apply to it to keep it steady, right? So, big result of this experiment, again, we've got a nice linear trend of the static friction relating the static friction to the normal force. Gives us this equation, the maximum static friction is equal to this value called the coefficient of friction that is specific to materials that are in contact, and it's multiplied by the normal force, directly related to the normal force, directly related to this coefficient, which is dependent on materials. Likewise, kinetic friction. Kinetic friction is equal to the coefficient of kinetic friction, that's the slope of this line that we would have got, times the normal force applied. And that's how we can now solve friction problems using those equations. So let's try a few. All right, so here we go. Now here's a table of the coefficients of friction for various materials. This is the mu s. Might be hard to read for you. Let's zoom in here. Right? My lighting is horrible. Mu s, mu k for different materials there. Copper and copper, steel and steel, oak and oak, etc., etc. So those are all experimentally determined. There is no way you can do an equation to figure that out. They all need to be experimentally determined. And so you'll either be given them in a table or asked to find it. So in this first question, we're going to do a couple basic questions and give you a couple basic questions. And tomorrow we'll try to do some harder ones. Here we go. What is the frictional force between tires on a 2-ton truck and the dry concrete road when skidding to a stop? So skidding, that means it's sliding. That means we're going to use kinetic. So we have to read and analyze. Have to understand first, what kind of situation are we in? Here we're in a sliding situation, so it's a kinetic friction situation. Now we have to figure out a bunch of things here, and they want to know, what is the frictional force? We know the weight of the truck is 2 tons. That is the weight. We know it's on dry concrete road. That's going to tell us the coefficient, right? So it's a truck. Trucks have rubber tires. So I'm pretty sure this is going to be rubber on dry concrete right here. Rubber on dry concrete. And it's skidding. So I know mu K is 0.7 right there. Rubber on dry concrete. K is for kinetic, for skidding. So I know the kinetic friction. So I've read, I understand it's sliding, I understand the materials that are involved. But to find that force of friction, right, the force of kinetic friction is mu K, which I got, times Fn. I need to find Fn. Well, we're going to draw a free body diagram or a force diagram for this truck. I'm just going to make the truck a block. Now the truck is touching the road, right? It's on a road, so it's touching the road. The road's going to push up on it with a normal force, and I need that normal force. If the truck is moving to the right, sliding to the right, velocity, I'm just going to note that its velocity is to the right, because that's going to tell me the direction of the friction. The friction will be to the left then. Now the road's touching it, this is from the road touching it, and then gravity, of course, reaches out and grabs you. So we've got the force of gravity, Fg, you could call that W for weight if you wanted to. So weight is either Fg or a W for weight. There's our forces involved. I need this normal force to find that friction. There's no other way to do it. Now, vertically, the forces are balanced. There is no change in motion vertically. So I know that Fg minus Fn has to equal 0. I took down as positive, up as negative, because my forces vertically have to add to 0. There's nothing going on that way. So the force of gravity is going to equal the normal force. It is not always equal to the normal force. Be careful about that. But it is a lot of times in our problems. Well, force of gravity, recall, was m times g. Well, we got a 2-ton truck. It tells us here 1 ton is 907, rather. 907.2. 907.2. Well, 2-ton truck, that's what, 1,814.4 kilograms. So that's going to be the 2 tons. So I got to figure that out. The weight is 2 tons, but then they tell us tons in mass. They're giving us mass. So that's a little discrepancy there. So that mass is 2 of these 907s. 2 times 907.2. That's the mass. 2 tons, 907.2 per ton. G, we're going to use 9.8 today. 9.8 for the acceleration of gravity. Plug that in your calculator, and we get Seems like a big number, but I think that's right. 1,000, actually 17,781.12 newtons of gravity. Now, since our truck is on level ground, it doesn't say that, but we're assuming that. That means the normal force and the gravity will be balanced because they're the only forces vertically. So they have to be balanced here because they're the only vertical forces have to be balanced. They're the only two, so they are the same. So there's our normal force too. That is the Fg, that's gravity. So that is our Fn. Be careful. Fg is not always Fn. Gravity is not always normal. It often is when we're in a nice horizontal situation like this, but it isn't always that. Now we plug that in back in here to this equation. Alright, you won't have the benefit of this, but I do. Alright, so that force of friction, Fk, will equal mu k, which I looked up there, it's 0.7, and then times Fn, 17,781.12. Plug that all into my calculator. Let's see what we get. 12,446.74. 12,446.784 newtons. Now that's way too many significant digits. We actually only have one significant digit up here for the 0.7. And the 2 tons is only 1. Right? Very little. So one significant digit wouldn't be reasonable. I should have rewrote this. So we're going to say that it's 12,400 newtons. We're going to go with 3 significant digits just because I said so, not for any good reason. All right, so there is one example of how to find friction. That's a long video just for one problem. We got to do a lot more. But you're going to watch this, you're going to do one problem like this, maybe 2 problems like this. And that's all you have for homework. Tomorrow we'll do a lot more.